Hello dear students, you are all welcome to this new dynamic channel Byte, where you'll be studying the notions needed for advanced level computer science and ICT and ordinary level computer science as well. Today we are dealing with advanced level computer science 795, the chapter logic gate. Let's start with lesson 1, a different logic gate, which is somehow the introduction. A logic gate is an electronic switch that implements a simple Boolean function. A logic gate is characterized by its Boolean function, that is the operator, and symbol. Each logic gate has a truth table it produces based on its input. As a nota bene, for a gate or circuit with I inputs, there are 2 to the power I possible possibilities on the truth table. Pay attention to this nota bene because when we shall be dealing in lesson 2 on the different logic circuit, we shall use this particular concept. So if, for example, I have 2 input, I'm expected to have 4 possibilities on my truth table. If I have 3 inputs, I'm required to have 8 possibilities on my truth table. There exist 3 categories of logic gates. The first category, primary logic gate. These are logic gates from which other logic gates are derived, and there are 3 of them: the AND, the OR, and the NOT logic gate. The first one, the AND gate. This gate performs logical conjunction. The output of an AND gate is 1 if and only if all its inputs are 1. First of all, before I proceed, at the definition, they said a logic gate is characterized by its Boolean function. When we talk of Boolean, we mean here that the only digit that we can have throughout this particular chapter are 0 and 1, because Boolean implies we are working only with 0 and 1. Now, the AND gate, as you can see, this is the symbol of the AND gate. This is the sorry, the expression. This is a truth table. From the expression, you see that the output S is A times B. So when you come 0 times 0, you have 0, 0 times 1, you have the result, and so on. The next one, the OR gate. This gate performs logical disjunction. The output of an OR gate is 1 when one or more of its inputs are 1. This is the symbol as you are seeing. This is the expression S is equals to A plus B. So when you're adding the different bits, you have the result. But when you come here, 1 plus 1, since you are dealing with Boolean algebra, and in Boolean algebra, 1 plus 1 is 1. The NOT gate. This gate takes a single input and produces an output that is the inverse of the input. And remember that, take note, this gate is the only logic gate that takes in one input, and the NOT gate is sometimes referred to as the logical inverter. So for a NOT gate, if I have as input A, then as output, I can have A complement as I can have A bar. There is a little problem with the truth table because the input being 0, my output should be 1. Input being 1, my output should be 0. So this is an error that has to be corrected. The second category, the universal logic gate. These are logic gates that can be used to implement any Boolean function without needing other gate types. There are the NAND and the NOR gate. In the lessons to come, we shall come back to this particular concept about the universal nature of the NAND and the NOR gate. But what you need to understand is that these are the only 2 gates that can be used to produce any other logic gate that is needed. NAND gate. This gate is obtained by adding an inverter, which is the NOT gate, to the output of an AND gate. A NAND gate gives an output of 1 if any of its input is 0. So now let me give you the design, that is the architecture of how the NAND gate is being derived. I have my AND gate, as you can see, its output is passed through the NOT gate. And we know that for an AND gate, as you have here, the output is A dot B. If I take this A dot B now and pass it to the NOT gate, my output is going to be A dot B bar. So this is how a NAND gate is being formed. Input A and B, output is A dot B bar. This is the abstraction behind it. For the truth table, we know that this is the truth table for an AND gate. And now, from this design, we clearly see that what this output is now passed to a NOT gate. When I pass 0, I have 1. Same thing for the other input. So that is how the truth table of a NAND gate is being derived. Otherwise, you can just decide to multiply, then you apply the inverter. Times 0, we give 0. We apply the inverter, we get 1. 0 times 1, 0. Apply the inverter, 1. Same thing for this and this. Now, the NOR gate, smart as you can be, just as the NAND gate was being derived, it is the same analogy we use to derive the NOR gate. It is a gate obtained by adding an inverter to the output of an OR gate. A NOR gate gives an output of 1 if and only if all its input is 0. That is the symbol. As you can see, we have OR gate with an inverter being added to the output. Expression A plus B bar. For the truth table, when you compare this and this, you clearly see that this output is obtained by inverting the different input of this particular one. So that's how we get it. Now, the third category, the exclusive logic gate. These are logic gates that produce an output based on the exclusive condition of their input. And there are two types, the XOR gate and the XNOR gate. Now, for the XOR, equally known as the EOR gate, this gate performs exclusive disjunction. So it's a type of addition. Exclusive disjunction. The output of a XOR gate is 1 if only one of its input is 1. Meaning that what? For me to have 1 on as output for a XOR gate, I must only have a single 1 as its input. If I have more than a single 1, I have 0. If I have no 1, I have 0. This is the symbol of a XOR gate, and that is the expression. As you can see, exclusive disjunction is a plus, which is encircled. Now, that is the truth table. As you can see, where we have a single 1, the output is 1. Where we have more than a single 1, 0. Where we have no 1, 0. The XNOR, also known as the ENOR gate, this gate performs logical equality. The output of a XNOR gate is 1 if only all its inputs are the same. That is the symbol for the XNOR gate, and that is the expression. Is just as for the NAND and the NOR, whereby an inverter is being added to the output of the XOR gate to get this. So guys, I expect from you to be able to produce the output of the XNOR gate and add it as a comment in the description to this video, and I will comment in order to validate or to correct those who might be wrong about the output of the XNOR gate. When it comes to exam purpose, it is very important for students to know the different conditions where each of these gates produces an output of 1 and when they produce an output of 0 as it is given in their description. Also, it is very important for you guys to know the symbols of each logic gate and the expression, because you might be given an expression where you'll be needed to derive the logic symbol. In lesson 2, when we shall be talking about the logic circuit, this notion we did today will be very important. Do not forget to like, subscribe in order to have immediate signal when another video of such is going to be posted, and share the link for other students who might not have access to the video to join us massively. In the description of my video, I will add the link to my WhatsApp group, my WhatsApp channel, for us to be participating in some exercises for you guys to prepare very well for your GC of this year. Thank you very much.